In this lesson, we're going to talk about solving system of equations still, but this time we're going to talk about another method called substitution. So in your previous method, you learned that you could solve by graphing and look for the points of intersection or point of intersection, and there were three possibilities. You could have one solution, which is where they met. You could have infinitely many solutions if the lines were right on top of one another, and you could have no solutions. That's also possible here. So those three scenarios are still possible here, but this is more of an algebraic method. So substitution says that if we're given two equations like we are here, right, they have a relationship to one another. So we can use one equation to help with another. In our way, substitution, what we're going to do is we're going to use the fact that we know what one of our variables is equal to. So y is equal to 2x, we're saying. So since y is equal to 2x, what we can do is we can say the first one tells us y is equal to 2x. Let's use that piece of information here in the second equation. So we're going to take the second equation, 4x minus y is equal to negative 4. And what we're going to do is we are going to take 4x minus our substitution piece was 2x is equal to negative 4. We're allowed to do this because the first equation tells us that y is equal to 2x. So since they are equal to one another, we can substitute those values in, substitute equal values in. We're not changing the value here. We can simplify. 4x minus 2x is just 2x. We have 2x is equal to negative 4. We can go one step further by dividing both sides by 2. And we're going to get x is equal to negative 2. So remember, like in the previous lesson, our solution was a point. So we just have to go back and figure out what's the y value, because we're going to represent this answer as a coordinate point, which our x value is negative 2, but we need to find our y value. Our y value you could plug x is equal to negative 2 into either of these equations up here above, either of the originals. One of these is easier than the others. We're trying to solve for y, and the first one says y is equal to 2 times x. So this one actually solves for y itself. So we could say y is equal to 2 times, well, we've now figured out that x is negative 2. So 2 times negative 2 is negative 4. So our answer is negative 2, negative 4. So what that means is if you graph both of these lines, what you're going to find is the point of intersection is at negative 2, negative 4. Let's look at the next example below. It might be possible that you don't have one of the equations already solved for one of the variables. All you need to do is solve for one of the different variables. So if I look at the first one, x plus 3y is equal to 7, I can easily make this an equation where it is either x is equal to or y is equal to. It doesn't matter which one you solve for first. So what I mean by that is if I subtract 3y from both sides, I'm left with x is equal to, and in whatever order you want to write this, you could write it as 7 minus 3y. That's the same thing as writing negative 3y plus 7, because that 7 was positive. Either way you want to write it, now what we have, we know what x is equal to, right? We know x is equal to 7 minus 3y. I'm just going to use that piece. And what I can do is plug that in for x in the other equation. So in the other one, we have 2x minus 4y is equal to negative 6. Let's use that first equation we just manipulated and say, well, we know what x is equal to. So this is 2 times x is really 2 times 7 minus 3y. So that was our whole substitution piece right here, getting plugged into that second equation. Minus 4y is equal to negative 6. So now we can distribute to get 14 minus 6y minus 4y is equal to negative 6. We can combine some like terms here to get 14 minus 10y is equal to negative 6. I'm going to solve for y, so I'm going to isolate the y on the left side here alone by subtracting 14 from both sides. We get negative 10y is negative 20. We finish this up by dividing the negative 10 to undo our multiplication. So we divide both sides by negative 10, y is equal to 2. So once again, our answer is going to be a coordinate point. We don't know the x value yet, but our y value is 2. So Now that you know what y is, you could plug y into either the originals or even into this piece right here, right? So that piece that we manipulated to find what x is when we had x is equal to 7 minus 3y, if you did your algebra correctly, that's the same thing as the first equation. We just manipulated by subtracting 3y from both sides. So you're going to have an equation that will solve for the other variable that you don't have yet. So if we take x is equal to 7 minus 3y, we could say x is equal to 7 minus 3, and we know y is 2. So 3 times 2. So this is 7 minus 6, which is just 1. So there we have it. We have our point, 1, 2. That would be our solution. If you were to do this, and you do not have to, but I wanted to show you, you could take either of the original equations. So if I take 2x minus 4y is equal to negative 6, and I plugged y in, I'm just going to show you that it doesn't matter where you plug in your y value into either of the originals here or the one that we plugged it in here. All right, you're going to get the same answer. So if we said, well, 2x minus 4 times our y was 2 is equal to negative 6, or 2x minus 8 is equal to negative 6. If we add 8 to both sides, because we're going to try to solve for x, we get 2x is equal to 2. Finally, we divide by 2, and we get x is equal to 1. And if you notice, that's the same as what we just got. So it won't matter where you plug it in, you're going to get the same answer. And all that work here in purple, you don't have to do. Great, we're going to work with some of these on the side up here. So your life is a little bit easier, definitely, if you already given an equation where it says one of the variables is equal to something. And so for the number 1, we're given that y is equal to 4x. So we can just take that and plug it right in for y into the second one, right? So we can take the idea that 4x is the same thing as y as the first one tells us. So this is 3x minus 4x. And I always plug in using parentheses just in case. And that's equal to 1. We can simplify this. 3x minus a 4x is negative 1x or negative x. We're not looking for negative x. We want positive x. So we can multiply both sides or divide both sides by a negative 1 to make it positive x is equal to negative 1. So that's step 1. Step 2 is finding the other variable. Either equation, I will tell you that this one will be easier since this is already set up to solve for y, right? This gives us y is equal to 4 times x. So y is equal to 4 times, we know x in this problem is negative 1. Y is negative 4. So our solution, we should write as a coordinate point here, negative 1, negative 4. On a graph, right, like from our last lesson, that means that would be our point of intersection. Good. Here in 2, it doesn't really matter which one you go with, but if you notice both equations are already set up for substitution. We know what x is equal to. We know what y is equal to. So that's going to be your choice. Let's go. I'm just going to use the second one because we've been using the first one the whole time. We know what y is equal to here, so we can plug it into the first. So we say y is equal to x minus 2. So if we take x is equal to 2y, bring that down, we're going to use the fact that the second equation tells us that y is equal to x minus 2. Right? That's where we use substitution here. We can distribute the 2 in. So x is equal to 2 times x is 2x, and 2 times the negative 2 is minus 4. If we subtract 2x from both sides, because we want to solve for x, I want to get all the x's on one side, we get negative x is equal to negative 4. Just like last problem, to get rid of the negative, we divide by negative 1, and we have x is equal to 4. Great, so there's part of our answer. 4 is our x value of our coordinate point. Let's find our y value. The second equation is solved, so y is equal to x minus 2. You could also use the first equation. The second equation is already solved for y. So we can get that y is equal to, well, x is 4 minus 2. Y is equal to 2. So here's our answer. If they're already set up here in 3, right? You're already set up for x is equal to in both of them, so it doesn't matter which way we go here, but we know x is equal to 2y minus 3. We can plug that into the second one. Okay, So if I take the second one, say we know x is equal to 2y plus 4, and the first piece tells us that x itself is 2y minus 3, we can say 2y minus 3 is equal to 2y plus 4. I'm going to start by getting the variables on one side, so I'm going to subtract 2y from both sides, and you're going to notice that something happens. Both the terms of 2y cancel, and you're left with negative 3 is equal to 4. So this gives us a false equation, right? Because this is not equal to one another. If this happens, right, where at some point you're given a false equation, right, your variables would cancel, this tells us no solutions. And if you remember from the last lesson, from graphing, no solutions occurred from parallel lines, right? So on a graph, this would look like parallel lines. And if you remember how parallel lines came to be, right? Parallel lines came to be from the slope, right? If you were to solve for both of these equations for y is equal to mx plus b form, right, our slope-intercept form, you would find that they have the same slope but different y-intercepts. So graphically, they never meet, which means no solution. So algebraically, this is what happens, is you're going to find one number is equal to a different number, which is not true, and then you can say no solutions. Let's try 5. Okay, one of the ones where we have to solve for one of the variables first. I'm going to take the first one. Let's take negative 0.2x plus y is equal to 0.5. It's probably going to be easier to solve for y since it doesn't have that decimal value on it. So what I could do is add 0.2x to both sides. And you're going to be left with y is equal to 0.2x plus 0.5. Right? Now we know what y is equal to. Here we're told what y is equal to. We can use the other equation and plug that into that one. So if we take the second one and say 0.4x plus y is equal to 1.1, we know what y is equal to. So we can say 0.4x plus, and then this is our substitution piece. We know y is, and I'm going to put it in parentheses just in case, 0.2x plus 0.5 is equal to 1.1. The reason why I'm putting it in parentheses is just in case there's a minus, right? If this was minus y, then you'd have to distribute the negative, the subtraction, into the entire set of parentheses. So I always plug in with parentheses just in case. Here, since we're just adding, the parentheses don't mean anything to us due to our associative property of addition. So we can combine like terms on the left side, and this is 0.6x plus 0.5 is equal to 1.1. We can subtract 0.5 from both sides. You always have a calculator to help you with your decimals if you would like, but what you're going to get is 0.6x is equal to 0.6. So I'm hoping that you don't need your calculator too much, because when we divide by 0.6, anything divided by itself will give us 1. So we have our x value. One more step is to find the y value. You can plug the x value into either of the originals up here, or you can plug it into the one you manipulated, because it still should be equivalent to whatever original you manipulated. So I'm going to plug it in here because this one's already solving for y. It has y is equal to. So we have y is equal to 0.2 times x, which is 1, plus 0.5. 1 times anything is itself. So we have y is equal to just 0.2 plus 0.5. And that leaves us with y is equal to 0.7. So our answer as a coordinate point is 1, 0.7. Awesome. Let's take a look at the next page. Mr. Randolph finds the supply and demand for gasoline at a station are generally given by the two equations. We're going to find where the equilibrium point where supply and demand lines intersect. Okay? So we need to just begin this by solving one of these equations for one of our variables. So I could just do this quickly on the second one. If I subtract x from both sides, and I'll bring it over here to the right, what I'm going to get is y is equal to 10 minus x. You could write that if you want as x plus 10. They mean the same thing. Okay? So now we know what y is equal to. From the second equation, what we can do is take, and this time I'll take the second one and we'll see how that goes, negative x plus 10, and we're going to plug it in for y in the other equation using substitution, right? So down here, x minus y is equal to negative 2. We know y is, and this is where we're plugging in, negative x plus 10. Pen dragged a little bit. It's equal to negative 2. So this is why it's so crucially important to plug in with parentheses, because we are subtracting this entire value of y. So we subtract the negative x and subtract the positive 10. So if we distribute that subtraction in here first, it's x plus x minus 10 is equal to negative 2, right? It's plus x because it's minus a negative x. We can combine like terms. 2x minus 10 is equal to negative 2. We're going to solve for x, so I'm going to add 10 to both sides. And we're going to come up here with it to get 2x is equal to 8. Divide both sides by 2. You get x is equal to 4. Great. One step away, once again, we're going to plug that value that we found into either of the originals, or in this case, you could also plug it into this one that we found over here, right? Because that's just an equivalent way of writing the second. I'm going to use the second one because it's solved for y itself. So y is equal to negative x plus 10, or y is equal to negative 4 plus 10. Y is equal to 6. So the supply and demand lines would intersect at 4, 6. It doesn't really give us what x and y are actually representing, so we don't really need to worry about units. Great, so one more. Sanjay is researching population trends in South America. He found that the population of Ecuador increased by 1 million and the population of Chile increased by 600,000 from 2004 to 2009. The table displays the information he found. If the population growth for each country continues at the same rate, in what year are the populations the same or predicted to be the same? So a couple things are happening here. You're given the 2004 population. We would call this like our starting point. Right? This is our first piece of information that we're given. Then you'll see we have a 5-year population change. Okay? So our 5-year population change here is a little bit different. We're going to actually break this down into a 1-year population change. So we're going to divide all of these by 5. Right? And what this is going to do is it will give us our rate of our population change per year. And remember, if this is our rate, if that's our rate, we call our rate our slope. So if we divide these by 5, since this we know what the population changed over 5 years, 1 million divided by 5 is going to give us 200,000. Okay, so 200,000, that means in Ecuador, the population increased 200,000 every year. In Chile, if we take 600,000 divided it by 5, you're going to get 120,000. So that's the population rate per year for them. We need to create our equations, okay? So our equation for Ecuador would be, if we think about y is equal to mx plus b form, our starting point is our b value, our slope is our m value. So we could write this as y is equal to 200,000. I need a little bit more space, I think, here. Y is equal to 200,000. X plus 13 million. Where Chile's would be y is equal to 120,000. X plus 16 million. So the good news is that both of them are equal to y, right? If they're both equal to the same thing, we can set them equal to one another, because that's substitution of us saying, let's just take what this y value is and plug it in for that y. And so essentially our substitution is us bringing this down. We can bring this down, and since they're both equal to y, we set them equal to one another and say 200,000. Got to make sure we have enough there. X plus 13 million is equal to 120,000. X plus 16 million. Okay, I'm going to try to solve this as quick as possible because this is a lot of zeros to be writing. So I'm going to subtract 120,000 x from both sides. And in the same step, and you don't have to put it in the same step, I'm going to subtract 13 million from both sides. I'm isolating my variable. We're having x on the left side. This will give us 80,000 x is equal to 3 million. So the question just becomes, when we divide both sides to solve for x by 80,000, what are we going to get? And this gives us 37.5. So you need to recognize what x represents because we put x and y in here. X is going to be equal the number of years. And y is our total population. And we don't really need to solve anything for y. It just says in what year will the populations be equal to one another. So we said it's going to take 37.5 years for the populations to be equal to one another. So you need to use the problem before and say, well, we know the starting point. We started in 2004. If we add 37.5 years to that, right, that's going to put us in 2041.5. The 0.5 doesn't really matter for us, right? Because that just means we're halfway through the year. So in year 2041 is when the two populations will be equal to one another.